All right, cool. Thanks for turning up. Bit of a late start, but we'll be all right. Okay, so back in 2016 in GDC, we did a live drive project with Epic and a few other partners. And this was the first time that, as a studio, we'd been exposed to kind of ideas of a formal look development workflow. And I kind of ran around and took some photographs in a key light and ambient light scenario of our actress Melina. But I think it's fair to say that we didn't really understand what we were doing. And since then, I've sort of seen, well, we've seen various talks that have look development as a component of a larger talk and give really good examples of why it's important, why it's a really established part of the VFX industry. The Human Race, GDC 2017, is a really good example. And it's been like, okay, great, but how do you actually put these things together? And so really, in our studio over the last year or so, we've been trying to kind of work on this and hopefully, as a result, improve workflows for our artists. So the basic aim in this talk is to give people, hopefully, the knowledge and the confidence to go out and hopefully implement some of these workflows for themselves. And in doing so, improve things for your own artists. So to give some context to the talk, it's useful to cover some of our ambitions as a studio. If you were in the Color Science talk earlier this afternoon, like some of these things will already be familiar to you. So ultimately, our benchmark should be film VFX. Clearly, there are some challenges still associated with real time, but when we're evaluating our assets, this is the benchmark that we want to set for ourselves. We also want to create some framework, some kind of methodology that's going to help us create assets that respond in a physically plausible way across all sorts of lighting scenarios, and also respond well to color grading. And finally, we want to make sure that our content looks great and the artistic intent is preserved across all sorts of different display devices, so SDR, HDR, and wide color gamuts, without having to branch assets. And we're also trying to change the mindset in the studio a little bit. So, we want people to ask themselves, does it look good, and does it look good for a game? And we want to get artists away from this idea that they're creating final frames at their desks, but rather creating a synthetic world that we're going to film with a virtual camera and then follow it up with grading and post. Critically, this shouldn't be seen as an attempt to restrict artists. We still want them to be creative. We still need them to use their artistic judgment because reproducing reality isn't enough. We want to create cinematic reality. So this is really about changing the process to improve the quality and not take control away. So how do we go about achieving our goals? So the core component is a series of look development environments. And these are environments, maps in UE4, that artists use to evaluate and stress test their assets across a range of different lighting scenarios. And so these environments have accurately calibrated lighting rigs that are built out of both HDR cube maps and UE4 lights. And we also use ground truth reference so we can assess how the real life counterpart to our asset responds to light in equivalent lighting conditions. So this process is completely reliant on digital photography, and so it's critical that we properly color manage the images we ingest. And so this means neutralizing color casts, correcting for white balance, and we also want to make sure that we're preserving all of the information possible, and that and additionally that we're also capturing the full range of light in the scene. For this reason, in general, it's better to only trust your own data because that's how you can be sure that it's being captured properly. So what does it give us? So it gives us a series of controlled digital doubles of physical environments, and we can use these to evaluate the look of an asset. So in this example, the ground truth reference on the left is shot in the physical environment, and this allows us to assess how the digital asset responds to those same lighting conditions. And that's shown on the right. That's not our shot, by the way, just in case you're wondering. What else? So it allows us to decouple lighting and shader issues. So the look dev environments have fully hopefully accurately calibrated lighting rigs. So if there's an issue, we know where to start looking. It's not going to be the lighting. All of the assets should be evaluated in the same look development environment. So this is about reducing the standard deviation. Like in the past, the situation has been a little bit like, like if you have a bunch of people like building a house, but everybody has a slightly different idea of how long a meter should be. It's like you're probably going to get it done. It's definitely going to be wonky, and it's probably going to take like twice as long. So we want to fix all that. And finally, it gives us a benchmark for reasonable lighting values, and we can go and use those as a starting point when we're lighting up levels and maps and cinematics and what have you. So, creating a look dev environment and optionally a set of ground truth images starts with the shoot. The shoot requires quite a bit of kit. As you can see on here, all of this is super essential. So you can use any decent quality camera, provided it has full manual exposure control, interchangeable lenses. You definitely want to be shooting in RAW format. And critically, it must have really good auto exposure bracketing functionality. We tend to use a Canon 6D because it's reasonably cost effective. It will take 7 bracketed shots out of the box, and you can expand that to 9 using Magic Lantern custom firmware. All of that equipment's obviously a bit of an investment. You can cheat a bit and save yourself like €800 by making your own calibration balls. So the critical part here is the paint. It has to be 18% grey. Basically, you're looking for Munsell N5 paint. Attach some handles, and away you go. I'm going to assume everyone knows the way around a DSLR or mirrorless camera, but there are a couple of points to mention. So the first is we always want to shoot in RAW. And this is because we are looking for the most faithful representation of the sensor data. We're preserving the full 14 bits of information. We're not crushing it down to 8 bits and chucking stuff away. It's not going to have lossy compression applied to it, and it won't have been sharpened or had contrast boosted by onboard processing. So secondly, the dynamic range, and therefore your auto exposure bracketing, or AEB, is really, really important. And so it's kind of useful to think about what we're doing here. We're not trying to take pictures, per se. What we're trying to do is use the camera to capture the full range of light information, such that we can accurately reproduce the lighting conditions in UE4. And so modern cameras, even really expensive modern cameras, are not able to capture the full range of light in a single shot. If we only capture part of the range, the lighting model is going to be wrong. PBR shaders expect PBR lighting intensities, so it's really important that we get this right. A set of 7 bracketed shots at 2 EV spacing, like in this example, is generally sufficient for most indoor scenarios. And as a reminder, a 1 EV change represents either a halving or a doubling of light, depending on which direction you're going. Shooting outdoors gets significantly more complicated. And the reason for this is just because there's a much wider range of light. Okay? And as I mentioned previously, we need to make sure that we're capturing the entire range of light in the scene if we're going to accurately recreate it in UE4. So we can't capture the full range using a single AEB pass of 7 shots, as in the previous example. So here we extend the range. We're doubling the range, in fact, by using a combination of neutral density filters on the lenses and an aperture stop, and that's dropping us down by 14 stops, and therefore expanding the range. So I know that you can't see it on this screen, but at minus 20V, the end one, you can actually still see the sun. And just to prove it, here is the merged EXR set to minus 20 EV, and that's displayed in Natron, which is like a free, really buggy version of Nuke. And so you can see at this point, right, we've still got really useful information about the light, even at this point. So before we shoot, we want to be evaluating the lighting conditions and also the subject type, and this is going to help us inform the camera settings that we're going to use. And we also want to do a scene survey. So at minimum, we're going to want to record the relative positions of the subject and the camera. If you're shooting indoors, you're at the very least going to want to record the ceiling height so we can accurately place the lights in UE4. You might want to take some other measurements as well. So the shoot itself generally consists of 3 parts. We've got a calibration shoot, and here we're going to shoot the color checker. That's going to help us neutralize color cast during image ingestion. And we're also going to shoot chrome and gray balls, and these are going to help us reconstruct the lighting in UE4. The second part is a light probe shot, and these are a series of fisheye shots that we're going to stitch into a panorama, merge to an EXR, and then color correct. And then there's the ground truth shoot, and these are the reference shots of our asset, and we're going to use those to help evaluate the asset against real-world lighting conditions. So the basic shoot layout is an 8-point circle of camera positions around a central point. The central point is where you're going to place the subject, the calibration devices, and also the nodal point of the fisheye lens when we're going to shoot the light probe. And you always want to make sure, like it's kind of easy to forget, but you want to make sure that everything's positioned at the same height as well. In general, I tend to aim for a 2-meter radius, but you might find that the environment forces a compromise. But either way, it's really important to note down the measurements so that you can recreate things properly in UE4. This is particularly important indoors, because in this situation, even a minor inaccuracy can have a really significant impact on subject lighting. The first thing we need to do is find the orientation layout. And I like to do this by placing the grey ball at the origin. And I walk around and I find a place on my 8-point circle that gives me like a really nice kind of lighting fall off from minimum to maximum intensity. This means that when we shoot the calibration board, it's going to give us a nice range of information, and we can use that to recreate the lighting. With a single main light source, like in this example, so it's outdoors, direct sun, like this is really straightforward. But obviously this can be less clear-cut in kind of more complex or ambient lighting environments. Before this shoot, we need to arrive at a base exposure value. And for anybody familiar with photography, like you're going to know that this is some combination of shutter speed, aperture, and ISO. And so to find this, we're going to place the balance card at the origin, angled towards the main light. And we're going to make sure it fills the frame, and then we're going to shoot one correctly exposed image. Now, the combination of shutter, aperture, and ISO that we arrive at is what gives us our exposure value, our EV. And this is now fixed for the shoot. Like your EV should never ever change. And so the particular combination of settings that you use to arrive at your EV is dependent on like a lot of different factors, like your light conditions, are they changing over time? Your subject type, that's going to affect what choices you have on shutter speed, for example. Either way, like it's always going to involve some sort of compromise. It's really helpful to use online depth of field calculators and exposure tables to kind of help. But the critical thing to remember here is you cannot change the EV partway through the shoot. You can change the shutter speed, the aperture, or the ISO, provided it gives you the same resulting EV. Okay, so at this point, we should have arrived at the base set of settings for the shoot. In general, well, not in general, absolutely, it's best to set the white balance to like a fixed number, so like 5.5K is fine. And this is so you can easily get the camera back to the same settings if you want to repeat the shoot. We're going to correct for white balance during ingestion, so it's not too critical here. Make sure your AEB settings don't exceed the shutter speed capability of the camera, and clip your brackets. I've done it more than once, and it's super annoying. And another thing that I didn't find out until, didn't realize until sort of fairly late was you want to disable image stabilization for bracketed shots, because otherwise it means that your brackets aren't going to align properly. Right, so after all this, we're finally ready to start shooting. So the first thing we're going to shoot is the color checker. Basically, we use this. So during image ingestion, we sample the RGB values on the patches, and we compare those values to like known reference values. From the differences between them, basically we construct a color transform matrix, and then applying this to the images in the shoot neutralizes any color casts. To illustrate what I mean by this, I've deliberately chosen a super extreme example that you wouldn't generally come across in real life, but this is the same balance card shot under different lighting conditions and with a different camera, and it should be pretty obvious that the color rendition is dramatically different. We want to correct for this. We don't want to be pushing incorrect color values into our pipeline. And this is a really good example of where you shouldn't trust like random images downloaded off the internet, because like you have no control of them. You have no guarantee that the color values are correct. And as the saying goes, crap in, crap out. You really shouldn't be doing it. So to shoot this, getting back to the shoot, to shoot this, you basically shoot it in the same position as the balance card. So we're going to place the color checker at the origin, we're going to angle it into the main light again, and we're going to shoot a full bracketed exposure. The second set of calibration data that we're going to shoot are the chrome ball and the gray ball, and these are going to give us the information we need to reconstruct the light. So the gray ball is at 18% gray, right? And this is as close to a simple Lambert shader as we can reasonably get. As Arno mentioned in his speech, like a sphere is really easy to create, digitally, so that's why it's a sphere. So the gray ball is going to give us information about the lighting intensity and direction. And the chrome ball, mirror-like finish, fully metallic. This is going to provide information that's going to allow us to orientate the HDR cube map correctly, and it's going to allow us to position the lights in UE4. So to shoot, we're going to place the gray ball at the origin. We're going to remember to set the height correctly, and we're going to put the camera in position 1. Once we've done that, we're going to shoot the gray ball using a full bracketed shot. And I'm going to swap the chrome ball in and repeat. Then we're going to move the camera to position 5, which is opposite side of the layout. And we're going to repeat the shoot for both gray and chrome balls. So after this, we should have 4 sets of bracketed shots. And we're going to later merge those into EXRs. And these are going to give us all the information we need to recreate the lighting. The second part of the shoot is the light probe. So to do this, we're going to place the camera at the origin, and we're going to shoot 5 sets of bracketed shots. And these bracketed shots are going to be merged into a panorama using PT GUI, and we're going to merge the result into an EXR. We're going to paint out the main light sources, and this is going to provide the ambient lighting and reflection contribution. So for the light probe, we want to fit the 8mm lens to our camera, the fisheye lens, and we're going to mount it to the tripod using the Nodal Ninja and Easy Levelers. And what these do, basically they're going to help us rotate the camera very quickly and very accurately around the nodal point of the lens, right? And this is going to make sure we don't introduce parallax shift issues, and it's going to give us a really nice stitched panorama and make putting it together and working with it in PT GUI a breeze. So you want to position the camera such that the nodal point of the lens is at the origin. Again, don't forget to check the height. The nodal point of the lens is where the colored band is on it. And so to shoot the light probe, we're going to shoot 5 sets of bracketed shots. So we're going to shoot 3 sets at 120-degree increments on the horizontal plane. So you're going to shoot, rotate 120, shoot, rotate 120, shoot again, and then you're going to bring it back to the origin. Going to rotate the arm 90 degrees and shoot up, and then rotate the arm 180 and shoot down, right? So we should have 5 sets of shots. Final part of the shoot is the ground truth, and these are the reference shots that help us evaluate our asset. Again, you're going to place the subject at the origin, and the number of camera positions and subject orientations very much depends on the asset that you're shooting, basically. So for a high-value asset, we will generally place the camera at position 1, and we'll shoot the subject on an 8-point rotation at the origin. And then with the subject static, we'll shoot the 7 remaining camera positions. You might also add micro shots for the eyes or any other kind of critical details you want to capture. For lower value assets, such as material samples, you might shoot an 8-point rotation just at positions 1 and 5. It really depends on what you're capturing. Okay, so now we have a memory card filled with bracketed shots of our calibration device, the light probe, and maybe a set of ground truth reference as well. So how do we go about correctly merging these shots into the EXRs that we're going to want? The EXRs that we need to implement our look dev scene and to develop our assets. So we process them using our image ingestion pipeline. So at a very high level, this converts the raw images into a useful format. And for this, for us, this is merged EXRs. And this is through a fully automated process. Specifically, it's generating archive quality images in an ASUS 2065 color space. As part of this, it's generating 16-bit linear TIFFs as intermediate files. And then from there, it's merging those files into the 32-bit EXRs. As part of this process, it's neutralizing color casts by generating and applying a color transform matrix. And then at the end, if we want, we can optionally rotate our 32-bit EXRs into a different color space. For example, sRGB, if the target platform doesn't support wide color gamut. And so there are three main paths to the ingestion. The first path ingests the color checker shots. And this is where we build the color transform matrix that we're going to use to neutralize the color cast for the shoot as a whole. The important thing to remember for this is the matrix is really specific to the lighting conditions, the camera exposure value, and the white balance settings. So if you go back and shoot under different light conditions, or you change those camera settings, this transform matrix is not valid. The second path is just a standard ingestion path. We use this for the calibration balls and the ground truth shots. And this is just merging to EXR and applying the transform matrix we generated earlier. The third path is pretty much the same as that. This is for the light probe. So it's basically the same as a standard path, except we're breaking out partway through to stitch the intermediate TIFFs into a layered panorama in PTGUI. So this is just the overview of the standard ingestion, and it shows the optional building of the color transform matrix if we're ingesting color checker shots. This shows where we temporarily break out of this process in order to stitch the panorama in PTGUI. And the important point to take from this slide is that we use the same code path for merging to EXR. We're not using the merging to EXR functionality in PTGUI. And the reason for this is just because of potential differences in the way the EXR is computed. We don't want to kind of accidentally introduce biases into our pipeline. So in PTGUI, essentially, if we're bringing in 5 sets of 7 brackets, as an example, we'd expect to output 7 16-bit TIFFs, so 7 stitched panoramas at the original exposure brackets. Going into kind of more detail, this is way beyond the scope of this talk. But if anybody kind of is thinking about trying to implement something like this themselves, hopefully this should give some kind of useful pointers of where to start. So the pipeline is written totally in Python 3. It needs to be 64-bit so that it can address sufficient memory for, mainly for the merging to EXR. Most of the heavy lifting, including the merging, is handled by the OpenImageIO lib. We use the color lib for pulling in reference color checker values, and that helps us construct the transformation matrices. We use DC-RAW exe with a custom wrapper for the raw to TIFF conversion. We use EXIF tool, again with another wrapper for the reading and writing of image EXIF and ICC metadata. And we also use PyZBar and OpenCV for some other bits. We tag the corners of our color checker chart with QR codes. And I use an OpenCV, we rectify the image, and this just automates the process of sampling the RGB values. This is version 2 of our pipeline. And implementing it represents, a not insignificant investment of resources and a half reasonable understanding of the problems that we're trying to solve. Version 1 was implemented with off-the-shelf software, and it trades some specific functionality against ease of implementation. So this is what we started with, and I would totally recommend doing this first. And so the process breaks down like this: you take the base EV only raw file of the color checker shot, and you need to convert that to a DNG file. And you can do that using Adobe GNV DNG converter. You bring that file into Adobe Profile Editor, and this is going to let you build a color neutralization profile, and it will also give you correct white balance and tint values. Then what you do is you open your entire shoot in Adobe RAW. You apply the profile you just created. You set your white balance, and you want to make sure that all your contrast, sharpness, sliders, what have you, are down to 0. From there, you want to export, save everything out as 16-bit TIFFs. Realistically, you're going to be using sRGB primaries. Then once you've done that, you want to import your TIFFs into Photoshop and merge your brackets into a final EXR. So the main limitations of doing it this way are a complete lack of automation. This makes it super time-consuming and potentially error-prone. Realistically, we've struggled with wider color gamuts in Photoshop, so to be honest, I sort of think you're restricted to sRGB doing it this way. And the final point is that the color neutralization step is done like midway through the pipeline on the TIFFs rather than end of chain on the EXRs. So potentially we're not getting quite as good a result there. So after we've ingested our images, we should have ground truth EXRs or our calibration balls and a panorama that looks something like this. And there are a couple of things we need to do before we can bring it into UE4. So we want to clean up the tripod using the clone stamp, and we also want to mask out the main light sources. And once we've done that, this is pretty much what it should look like. The reason we want to mask out the main light sources is because this is only going to be used for the ambient light contribution. We're going to recreate those light sources we've masked out using standard UE4 lights, and this is going to give us the closest match in UE4. The example given here is pretty straightforward. There's just two light sources to mask out. Something like outdoor sun, again, very easy. You mask it out, replace it with a single directional. With more complex environments, you need to make some decisions about what you consider your primary lights that you're going to mask and recreate, and those that you consider kind of background lights that you're going to leave in the HDR. You know, and it might take a few iterations before you kind of arrive at a nice result. Once you've done this, you want to save it as a .hdr file. And when you import that, UE4 will automatically create a texture cube asset. And this is what you want for a cube map. Keep everything else as EXR, and they'll come in as just straight HDR textures. Right, so if I can go into UE4. Yay. Right, so. Okay, so moving into UE4, the look dev environment itself is basically made up of two really simple blueprints. So BP Light Studio here, this provides the framework for setting up our lighting rig using both the HDR panorama and the UE4 lights. So here we assign the cube map, we toggle its usage, we modify its intensity, and we control its orientation. Then we have a BP calibration device. So this contains digital doubles of the calibration balls and the image planes that we're going to use to display our reference EXRs. And we're going to use this to basically orientate the cube map, place our UE4 lights, and calibrate the lighting intensities of both. So the BP Light Studio just has a handful of exposed variables. So we can toggle the HDR array, we can modify the brightness. Wow, that's really slow. And we can assign the cube map here. Underneath the blueprint scene component is where we parent our UE4 lights. The rotation of the cube map is driven from the rotate Z channel on this. It's remapped to a 0 to 1 range and put into the material. This means that by rotating this, both the cube map and the UE4 lights are always going to rotate together. You're not going to get them drifting apart. The blueprint, the light stage blueprint, has just got two components. It's got the skybox, which is just a static mesh. It's a sphere scaled up massively. So this is going to hold our HDR cube map for a dynamic material instance that's going to be created and assigned in the blueprint. The skylights component is, everybody here is going to be really familiar with this. It's set to movable and SLS scene captured. So this is going to capture information about the, it's going to sample a scene, in this case our cube map, and it's going to apply it as light. There's nothing remotely complicated in the construction script. So here we're just storing some rotational values for use later. We're creating a dynamic material instance with a switch so we can toggle it on and off. We're assigning the material instance to the skybox. We're assigning the cube map, and we're setting the brightness, and then we're taking the rotation of the scene component, retargeting it to a 0 to 1 range, and we're throwing that to our skybox material. After all this, because the skylight rather is set to movable, and because we're modifying the lighting, we need to recapture it so those changes are reflected. The material for the skylight is similarly basic. It's basically a stripped down version of one that already exists in the samples asset. So here's just the param cube. This is going to take the cube map, runs out through a multiply node. This is controlling the intensity. Into the UV coordinates is the normalized output of a rotate about axis node. And here we're just setting the axis that we want to rotate around, so that's Z. We're defining a pivot point and a position. And then here we're feeding the rotation in a 0 to 1 range, and that's what rotates the cube map. So the second blueprint is the BP calibration device. So as I've said, this contains the digital versions of our calibration devices. So here we can just assign AXRs for our reference, and we can change the properties of the calibration device to match the configuration of the device in our chute. Again, there's nothing particularly complicated about this blueprint. We've just got 4 static meshes. We've got grey ball, chrome ball, and we have the reference cards that take the material holding our reference AXRs. So this is just an unlit material with a linear sampler type. The grey ball material has a base color of 0.18, a spec of 0.07, and a roughness of 0.85, and we think this is a reasonably close approximation of the paint on a physical counterpart. All right, so let's use all these to set up a LookDev environment. So the goal here is to match the lighting on the digital calibration balls to that in our ground truth reference. And once we've done this, we can be confident that we've accurately replicated the lighting environment in UE4. So I have already imported our calibration shots. So we have the grey ball AXR from camera position 1 and camera position 5, and also the chrome ball here. And in here, we've got the texture cube asset. That's our HDR panorama. Okay, so I'm going to start by assigning that to our scene. So that's has come in like that. And I want to assign our ground truth reference to the calibration device. And basically, I'm going to use the chrome ball to begin with, and this is going to help us. Tell you what, one thing I do need to do first. You want to turn off all your post-processing apart from the tone mapper. Right, okay. Let me just boost the intensity on that so it's ordering. Right, okay. So the first thing we're going to do, right, is we're going to use the chrome ball to orientate the cube map. So you can see that the cube map is reflected on our digital chrome ball here, and the idea is that we want to match it to our ground truth reference here. And so the way we do that very simply is to rotate the blueprint scene component for the lighting rig. And I happen to know that it's approximately minus 0.75. And so you can see that, like now, the reflection on the digital ball matches our ground truth reference, right? So the second thing we need to do is to position the UE4 lights, and we want to position them over the masked regions in our HDR. So if I turn them on, you should be able to see that the highlight is reflected in our chrome ball, and we're going to use that highlight to correctly position the UE4 lights. Now, because I did a scene survey, I happen to know that the height of the ceiling is 260 centimeters. So we're going to put that in. Without that information, like, you can't really position these properly. And then from there, I'm just going to use the axon Y to position it until the highlight is approximately over here. So you don't have to suffer me fiddling about with values. I happen to know that's minus 72, minus 24. All right. So once once you're kind of happy with that position, I'm going to go back and over here. I'm just going to position the second UE4 light, and it needs to sit over this masked region here. So 14 right? And so once you're sort of fairly happy with, once you're kind of really happy with the orientation of your cube map, and you feel like you've got your UE4 lights in the correct place, now we're going to move on. We're going to use the grey board to calibrate the lighting intensity of all these. Oops. So I'm going to select the calibration device and enable our grey ball. And I'm going to go into HDR adaptation mode. And the reason I'm going into this mode is because I want to use the pixel sample at the center of the screen. So this is going to give me scene referred luminance values underneath this cursor in the middle. And so the basic idea is that I'm going to sample an equivalent point on my reference, and I'm going to look at the luminance value it's given me. And I'm going to come down here on my digital grey ball, and I'm going to modify the light intensities until they match. I like to try and calibrate the intensity of the HDR first. And what I'm going to do is I'm going to sample the luminance value in an area that's in shadow. So this is an area that's not really affected by the lights that we're masking out and recreating. This is like pretty much from an ambient contribution only. So I'm going to position it there, and it's given me a luminance value of about 0.012. So I'm going to find an equivalent point down here. I'm going to go to my Light Studio, and I'm going to basically bump this until it gives me 0.12. And you know, I can go back the other side. I can check against the ground truth reference from camera position 5, and we can sample from this side as well and kind of further refine it. So once I'm happy with the intensity of the HDR, I'm basically going to follow the same process for each of the UE4 lights. So I'm going to start with the softbox light here, the one at the front. So I'm going to turn that on. I also need to remember to make sure I'm checking the correct EXR. So I'm going to find a spot here that's receiving a lot of influence from the light that I'm trying to tune. So I'm going to go here, and it's going to give me about 0.23. So I go to an equivalent point in here. I boost the intensity. 0.65. Until I'm kind of happy that what I'm seeing here is as close as I can get to my reference, right? And then basically it's the same for the final light. So I could have made this calibration blueprint better so I didn't have to keep switching images. Right, so the second light is mostly influencing like the rear center of this. So I'm going to sample the center of our reference here, which is about 0.07. And then basically kind of up that until it matches. And like, you know, I sort of set this scene up before and kind of have a good, reasonable knowledge of what the values should be already. In general, you take like quite a lot more time and care over this. It's an iterative process really, and how long it takes depends very much on like how complex the scene is. You might even find that you need to go back and change the masking, go back into Photoshop and like change how you've masked the HDRs. But essentially that's the basic setup complete. That's how we calibrate our lighting intensities. And hopefully, if I actually change to the correct one, you know, we should at this point feel pretty confident that the lighting that we've calibrated in this scene is as close as we can reasonably get to the lighting in our actual physical environment. So once we've done this, we add it as a sublevel to our master look depth scene. And here we've just got a bunch of extra functionality. So my controller is not working. Wonderful. Right, okay. You have to take my word for it. we've got a bunch of extra functionality. We can use to switch between free cams. We've got we can go into a fixed camera mode that basically replicates the 8-point shoot layout, and we can switch. That's really frustrating. That's not working. Basically, we can cycle through the different lighting environments that we've constructed. And like right now, we're using this methodology and these look dev scenes to kind of help our artists improve the quality of the assets that we're pushing out and kind of reduce the problems that we had been experiencing on previous projects. Looking beyond this, the intention is to basically build an automated system on top of this that is going to basically scrape the database for assets, either new or updated assets. They're going to automatically put them into these look dev scenes and then render out, create review renders, so that in the morning, artists can pick up these renders and we can review the content in our daily reviews. And possibly, the other intention, once we got to that point, we're looking at integration with Shotgun to kind of help our production workflows as well. So that's kind of basically it. There's one caveat actually with the HDR visualization mode, which I realized at the weekend when I upgraded the engine, is that this is running on 420, but in 421 upwards, it doesn't actually have the pixel sampler, which is quite a problem. In our own studio, actually, we've written our own pixels sampler that's not reliant on this. Yeah. Anyway, hopefully the information here is kind of useful for you guys to think about setting up your own kind of development. Maybe you can find a room in your studio where you've got lighting conditions that are the same, like no matter what time of the day you go in there. That's really useful because if you want to go back and repeat a shoot, you really want to have the same lighting conditions. But yeah, that's kind of it. Awesome. Well, thank you very much.